So now let's talk about the idea of respiration versus breathing. Respiration, in a biological sense, is really referring to how we use oxygen to create energy. Excuse me. In general biology, you learned that this was referred to as aerobic respiration or aerobic cellular respiration. Now, since aerobic cellular respiration is where the oxygen is used, that's kind of where we get the respiratory system and the use of respiration as defining or as our generic term for the respiratory system. Now, respiration itself is technically this use of oxygen for the production of ATP along with glucose, of course. But in order for us to have the oxygen necessary to accomplish this chemical reaction, we need to get that oxygen to and from our lungs and into our blood, into our tissues. The first part of that process is breathing. Now, of course, the need for oxygen is what drives the breathing process. Okay? Now, breathing itself is simply the exchange of oxygen and carbon dioxide with our environment. If we break it down, what we see is that there's three general steps to this process. First, we have pulmonary ventilation, which is getting the air to and from our lungs. From then, we then need to take and get specific gases into our lungs and out of our lungs, namely oxygen into our blood and carbon dioxide out of our blood via the lungs. And finally, once we've put that oxygen into the blood, we then need to deliver it to our tissues and drop it off. That is the third mechanism here associated with respiration, and that is internal respiration. Excuse me. Now, if we take a closer look at pulmonary ventilation, which is the first step that we're going to discuss, this involves two processes. We have inspiration and expiration. Inhalation and exhalation. They are interchangeable. Now, what we've learned one of the concepts we've learned thus far is that substances tend to passively move according to a concentration gradient. But when talking about gases, we more often refer to a pressure gradient. That is the primary reason gases move. Gases will always move from an area of high pressure to low pressure, which means if we're going to get gases to move into and out of our lungs, we have to create a pressure gradient. Yet, how do we do that? Well, we've got two options. If we take our little guy here and draw him, he's got his little, that is a really bad drawing. Let's give him a little nose. That kind of looks like a guy, right? I know, funny. So we need to get the gases into this guy's lungs, right? So his lungs are around here. Well, in order to do that, to sort of make the gases go in, we need to make the pressure in our lungs lower than the pressure out here. Okay? We have two options, or two ways to do that. We can either increase the pressure around us or decrease the pressure within us. Now, since we have no way of manipulating the pressure of our surrounding environment, our only option is to decrease the pressure within our lungs and within our thoracic cavity. Now, what we see is we have the ability to do that according to a gas law known as Boyle's law. Boyle's law is described by this diagram, which basically states that volume and pressure are inversely related to one another. Okay, which means as volume increases, pressure will decrease, and vice versa. As volume decreases, pressure will increase. Now, what this has to do is with the fact that all molecules in a gas are in constant motion. If you look in this chamber here, Each of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 molecules have a whole bunch of room to move around in, which means they're less likely to bump up against one another or bump up against the sides of the glass. If, on the other hand, we take and decrease the size of that chamber by half, what ends up happening is each of these 13 molecules now have less space to move around, so they're going to bump against the glass much more often and bump up against each other much more often, which causes the pressure to rise. Okay. Now, keep in mind, we could get the same result by adding 13 more molecules to the same space. Now notice, by adding all of these extra molecules, we're kind of getting the same effect. Each individual molecule has less space, which creates an increase in pressure. Both of these ideas are going to be used when talking about the pressure changes associated with inhalation and exhalation. Okay? But the basic concept here is the pressure of an individual gas is related to how much space it has to move around. The less space that gas has to move around, the higher the pressure. Whether that less space, so to speak, is due to a decrease in volume or whether the decrease in space is due to adding more molecules. Either way, we get the same result and have an increase in pressure. So what does this mean for respiration? Well, in order for respiration to occur, we need to make the thoracic cavity bigger. Well, in order to make, so for inhalation to occur, we need to decrease the pressure within the thoracic cavity, or within the lungs, I should say. We do that by increasing lung volume. Not lung volume, but thoracic volume. So we do this by dropping our diaphragm primarily, and lifting ribs. Now, many of you have taken lab already. And what I want you guys to think about is for those of you who are taking lab, think back to that cat dissection. Okay? So with that cat dissection, you guys identified the diaphragm and you identified the lungs. So what we're saying here is we can drop the diaphragm and lift the rib cage, and this makes the thoracic cavity bigger. Problem is, we don't need just the thoracic cavity bigger, we need the lungs bigger. Now think back to that cat. Are the lungs actually attached to the thoracic cavity? Hopefully you're saying no, they were not physically attached. You didn't have any strings, you didn't have any ligaments, you didn't have any of that stuff. So how can it be that a drop in the diaphragm makes the lungs bigger so that we can get our pressure change? Well, let's go ahead and take a closer look at this. So here is our trachea, right? And here is our lungs associated with that trachea and bronchi, right? Okay, so that's our lungs. Remember, if we go back to our anatomy, on top of the lungs is going to be our visceral pleura, right? The visceral pleura would then be in contact with the parietal pleura. And finally, the parietal pleura would be in contact with our thoracic wall, either the diaphragm down here or the ribs here. So, if we are going to have a change in lung volume corresponding with a change in thoracic volume, then we need to establish three connections. We need to establish the first connection between the lungs and the parietal pleura, the second connection between the visceral pleura and the parietal pleura, and finally the third connection between the parietal pleura and lungs. If we establish these three connections, then whatever the diaphragm and ribs do, the lungs will move right along with it. So let's list these out. So we need first connection between the diaphragm and the parietal pleura. Next, we need a connection between the parietal pleura and the visceral pleura. Finally, our third connection between the visceral pleura and the lungs. If we can make this connection, then whatever the diaphragm does, the lungs will do. Well, we already have explained one of these, if you recall. In the last lecture, we explained that the parietal pleura and the visceral pleura were basically stuck together. Thanks to the adhesive and cohesion of the pleural fluid. Okay. The question is, how do we explain the connection between the visceral pleura and lungs and the diaphragm and the parietal pleura? Well, that has to do with the arrangement here. Now, if we blow this up, what we're going to see is we kind of have the ribs here. Then we have parietal pleura here. Then visceral pleura here, and finally our lungs, right? Same colors. Now, what we then find between all of this, as we saw earlier, is our pleural cavity. Okay. Now, this pleural cavity is a cavity that has its own specific volume measurement. And since it's a confined space, it also has its associated pressure. Now, because of the arrangement of the pleural cavity and inside the lungs, it gets slightly stretched. And because that volume gets slightly stretched, its pressure gets slightly lowered. So the pressure within the pleural cavity is slightly lower than what you would expect. Now, if we take the pressure around us in the atmosphere, the pressure around us is about 760 millimeters of mercury. Now, before inhalation and after exhalation, the pressure within our lungs is also 760 because air is not moving. But because of the orientation of the pleural cavity, the pressure in here is slightly less, about 756. What ends up happening if we compare, remember, the pressure outside the ribs is 760. The pressure inside the lungs, which is right here, is 760. So what ends up happening is these pressures end up pushing on each other because they're different. These differential pressures create a situation where they push against one another, creating a pressure gradient referred to as a transmural pressure gradient. This is true for down here as well. Okay, so imagine if I ask you to take your two hands and put them on either side of your textbook, flat as can be, and press against each other. Well, your left hand would be pressing against your book, pushing it into your right hand. Your right hand would be pushing against the book, pushing it into your left hand. Well, since you're pushing against the book from opposing sides, you can technically lift that book up without actually holding on to it. That differential pressure that's happening when you're pushing against each other is the same idea as what's happening to these transmural pressure gradient. And this is ultimately what causes the final connections that are necessary in order for the diaphragm to move in conjunction with the lungs. This also explains the concept of a pneumothorax, or collapsed lung. If for whatever reason we have injury that causes a breach in that pleural cavity, well, the second that pleural cavity is no longer separated from the environment or the lungs, the pressure is allowed to equalize. Well, once this pressure gets up to 760, we lose the transmural pressure gradient and the lungs fall away from the thoracic wall. And that's what we refer to as a collapsed lung, where we've lost that transmural pressure gradient and we no longer have the connections necessary for the lungs to move along with the thoracic cavity. Now, this is what is being demonstrated by this diagram here. The pressure within the pleural cavity is slightly lower than both the lung pressure and the external atmospheric pressure. This creates that pressure gradient that forces the parietal pleura to adhere to the lung wall and the visceral pleura to adhere to the parietal pleura to adhere to the thoracic wall, and the visceral pleura to adhere to the lung wall. So now let's talk a little bit about what's happening during inspiration. So in order for inhalation to occur, we need to make the size of the lungs larger, the volume of the lungs larger. In order to make the volume of the lungs larger, as we make the volume of the lungs larger, the pressure within the lungs is going to decrease. So let's take a look at how this occurs. So let's start up here with step number 1. At this point, we are done exhaling, but we have not started our next inhale. Okay, so what this means, if we take an individual alveolus like this and draw it out, okay, we're going to make these changes in reference to the a single alveolus, but realize this is happening to all alveoli and to the lungs as a whole. Okay, now at this point, there is a specific amount of air left inside this alveolus. Okay, but because air is neither moving in nor out, that means the pressure outside, which we learned is 760 approximately, is the same as it is inside, which is 760, which means no air moves. Now, in order for inhalation to occur, we need to drop the alveolar by increasing the alveolar volume. Okay, so what ends up happening is we increase the alveolar volume. This is done by One, contracting the diaphragm. As well as contracting the external intercostals. This makes increases the volume of the thoracic cavity and with 3 connections that we just mentioned that I don't have space to rewrite here, but add them in on your diagram. So with the 3 connections previously mentioned, we also see an increase in lung volume. Okay? So this increase in lung volume causes our decrease in pressure. Okay? So what ends up happening, we go from 760 to 758. Well, at this point, the pressure inside is lower than the 760 outside, so air flows in. So this air will continue to flow in until added air increases alveolar pressure to 760. So if we draw this guy over to here to include the added air, okay, so we're going to redraw it to be about the same size, hopefully. So they're meant to be the same size, but now we have all of this extra air. Okay? And this added air brings the pressure from the 758 that it was to the 760. So again, now that we're 760 here, we're 760 out here, we have equal pressures. Means equals no air movement. Well, now it's time to exhale. Okay? So in order to exhale, we need to increase alveolar pressure by decreasing alveolar volume. Okay. Now how do we do this? Well, first thing we do is we relax the diaphragm and intercostals. Okay. This relaxation stops the lungs from expanding, but it doesn't cause them to exhale. In order for exhalation to occur, we rely on the elastic connective tissue embedded throughout all of the lungs, as well as the surface tension of the surfactant causes lungs trying to make sure I have enough space here to shrink to original size. So if we redraw this, what we're going to see is we're going to shrink to our original size, which is about like that. Not quite. I think it's maybe a little bit bigger. Okay, but here's the thing. If I'm returning to my original size, why aren't I returning to my original pressure of 760? Well, what's different about these two? Well, I may have returned to my original size, but I returned to my original size with extra air. Well, that means original size with extra air means higher pressure. So all of that extra air creates a pressure of 762. It's still 760 outside, which means air is going to leave. Wrong color. So air is going to flow out. And this continues. So the air flows out until enough air is left to drop the pressure back to 760. Okay, so this process brings us back to our beginning here, and we repeat. So we're going to go back and review some of these concepts in the slides that I had made, but if you're not ready to move on and you're still taking notes, go ahead and pause here until you're ready to move on. So as I said, the inspiration or inhalation process occurs when the alveolar pressure drops below the atmospheric pressure. This drop in alveolar pressure is a result of an increase in thoracic volume. Let me go ahead and return my ink color to something noticeable. This increase in thoracic volume occurs due to contraction of the diaphragm and the external intercostals. This makes the thoracic cavity bigger. Now, the thoracic cavity transfers its increase in size to the lungs, okay, via those three connections that we discussed previously. The three connections being the diaphragm and parietal pleura being connected via the transmural pressure gradient, the parietal pleura and visceral pleura being connected via the adhesion and cohesion of our pleural fluid, and finally, the visceral pleura and lungs being connected again by the transmural pressure gradient. Once the lung volume has increased, the alveolar pressure will decrease and air will flow in. Exhalation occurs under resting circumstances completely passively. You should have noticed on the previous slide that in my previous diagram that there was absolutely no physical action being taken for the process of expiration. It was completely passive, and it relied on two things: the highly elastic nature of the lungs, and the surface tension of surfactant. Okay, both of those two characteristics will naturally cause the alveoli to return to their original size and their original volume. Once they return to their original volume, the extra air causes an increase in pressure above atmospheric pressure, causing the air to flow out of the alveoli and out of the lungs. Now, this process here is another diagram that summarizes what we just talked about. The only thing you're going to note is instead of using 760, 758, 762, what it does is uses positive 1, 0, and negative 1. Now remember, gases move from high to low. So if we are 0 out here and negative 1 in here, gases are going to move in. If we're 0 and 0, no gases are moving. If we're 0 and 1, gases are going to move out. But this diagram is basically the same thing I drew previously. And it's for your information and review if you would like to get a different interpretation of the process. Now, what we just talked about was normal everyday breathing, the breathing that's constantly occurring when you're not even thinking about it. We do, however, have the ability to manipulate breathing to a certain extent. You can take a deep breath if you're feeling stressed out, or you can blow out a candle if the scent is bothering you. That's accomplished through forced inhalation and forced expiration or exhalation. The process of forced inhalation and exhalation uses additional muscles that create a greater volume change, because remember, the greater the volume change, the greater the pressure change. So we can get a greater volume change for inhalation by getting more use out of the external intercostals as well as the scalenes and sternocleidomastoids, which get a greater lift on the rib cage. The greater the lift on the rib cage, the larger the volume and pressure change. For forced exhalation, what we typically do is contract our internal intercostals and our abdominal muscles. By contracting our abdominal muscles, we force all of our abdominal organs up against the diaphragm, which invades a little bit of that thoracic volume, getting an even smaller thoracic cavity, and as a result, a bigger pressure change. Now, lung compliance is something I'm going to want you to read about in your book, and it's just the concept of how easily your lungs accomplish what they need to do. So make sure you read over this section in your textbook and be ready to answer questions about it on your quizzes and exams. Finally, we have a discussion of airway resistance. Well, if air is moving through a tube, well, blood was moving through a tube, and several characteristics of that tube created resistance. Well, the same can be said here for airway resistance. The ease at which you breathe is directly related to the diameter of your airways, and your body will actually manipulate that diameter as necessary. This is particularly done during sympathetic stimulation when we increase the diameter of our airways, make our airways wider, which makes breathing easier. Now, when you have decreased sympathetic stimulation, your airways return to their original size and breathing becomes slightly more difficult. Typically nothing noticeable for an average individual. Okay. Now, this bronchial dilation, as it's called, occurs when the sympathetic nervous system activates beta-2 receptors. As you recall, beta-2s and alpha-2s are inhibitory. So when we activate that inhibitory receptor, we stop the muscle contraction, and if we stop the muscle contraction, the bronchioles will dilate. So this is what happens when you're running from a bear. Okay. Now, airway resistance can be manipulated through bronchial constriction and bronchial dilation via the smooth muscle, via manipulation of the smooth muscles that surround the bronchioles. This diameter, however, can also be manipulated or be affected, I should say, and airway resistance can also be affected by anything that is found coating the bronchioles. Okay, so your drain will drain faster if you have a larger diameter drain, or if you don't have big hairballs lining the drain. Same principle here. This is why when you get bronchitis or you get any type of lower respiratory tract infection, it becomes more difficult to breathe because the added mucus decreases the diameter of your airways, creating a harder breathing situation. So as we finish up this lecture, let's answer a few questions. Which of the following explains the connection between the lungs and visceral pleura? Adhesion, cohesion, pleural ligaments, or transmural pressure gradient. Take a second and think about it. Hopefully what you guys are leaning towards is the transmural pressure gradient. Remember, this is where we have that differential pressure within the pleural cavity compared to the lungs or external environment, creating our connection there. Notice the double asterisk. This means there are multiple answers, multiple potential answers, so take a second and read through these and see what you come up with. So, exhalation is completely passive, requires contraction of the diaphragm, occurs when respiratory muscles relax, results in a decrease in pressure causing air to leave the lungs. Well, of all of these, the ones that are correct would be A and C. Remember, contraction of the diaphragm is for inhalation. And a lot of students will choose D because they see air leaves the lungs. Well, yeah, that happens during exhalation. That's got to be it. But would air leave the lungs due to a decrease in pressure? Hopefully, for those of you who are thinking this was true, you're thinking, oh, crap, I didn't read that part. So remember, for this to be true, it would have to be an increase in pressure. So the last thing we're going to talk about, or you're actually going to talk about on your own, is lung volumes and capacities. I do expect you to read through this on your own and be familiar with all of the major lung volumes and lung capacities associated with this section in your book and associated with the diagram. I thought the diagram was on the next slide, but it's not. So do make sure you read over lung volumes and lung capacities and be familiar with this. Other than that, that is the end of Part B of your lecture. Next section, we'll talk a little bit about the chemistry of what's going on and how the gases are actually transported in the blood.